All right, so I logged into Blackboard. I checked on the quizzes. I think we're good to go today. So the quiz email or invitation will be sent out in 15 minutes. So before that, I'm just going to finish up a couple of items from lecture set number 6, which we started on Thursday when we were supposed to have the quiz, but we couldn't because of the login issue. All right, so in lecture set number 6, we have been discussing the completely randomized block design. So as a refresher, the completely randomized block design is an extension of one-way ANOVA, where we have one treatment effect, we have one response variable, and we introduce a blocking effect. And the block is meant to pull out information from a confounding variable. So we are trying to account for a variable that we know is present in the experiment, but we do not want to study the effect of. And that's, again, the purpose of said block. All right, so we went through a few illustrations of how to compute different sums of squares. This is relevant because on assignment number 4, you're going to have to do these types of calculations. And then we looked at a completed example of the test for treatment effect based off of a CRBD, which runs in exactly the same way as a one-way ANOVA. So we have essentially the same null and alternative hypotheses. Our test statistic is computed through an ANOVA table, but in this case, it's a completely randomized block design ANOVA table rather than a one-way ANOVA table. And then our conclusions and decisions about H0 are conducted in the same way using the F table or the p-value approach. We left off looking at an example where we wanted to compare the results of one-way ANOVA to the completely randomized block design. Now, there are two key aspects to this example. The first one is noticing the similarities between the one-way ANOVA table, which I have on slide 17, and the completely randomized block design table, which is on slide 15. In particular, you'll notice that the column for the total and the treatment are the same for the CRBD and the one-way ANOVA. Okay. So if we just take a quick mental picture here, we have 23,506.33, 5, 201.32, 40.26. When we scroll over, you can see that those numbers are exactly the same. So 23,506.33, 5, 201.32, 40.26. What changes is the error column. You'll notice that the sum of square error is now larger with the one-way ANOVA than it was with the CRBD. And again, this is a result of the block essentially pulling information out of the, pulling information from the confounding variable out. So as a result, what you'll notice is the p-value or the F statistic is smaller for the one-way ANOVA and the p-value is now larger. Now, in this case, we still have a significant result. So if we were to complete the test very quickly here, we would have p-value equals 0.0257. So we would reject H0. And then we could say at the 5% significance level, we have, or the data provides, so to suggest, and then we would have the same conclusion given on slide 16. evidence of a difference in the average content found in wheat at the 6 different treatments. Okay. All right, so again, the keys here, if we were to summarize, okay. So they have same SST, SSTR, DFT, DFTR, and MSTR. Okay, so they have the same total. They have the same sum of squared total, the same sum of squared treatment. They have the same degree of freedom total and the same degree of freedom treatment, and they have the same mean square treatment. They would also have the same mean square total, but we don't use that value, so I'm not going to mention it. Okay. And then we would say for CRBD, F value is smaller if blocking is useful. Okay, so if we include the information from the block, this will, as a result, reduce the F value for the treatment effect. And this is true because if the block is useful, it's pulling information out from the confounding variable. So that would mean for a CRBD, the block being useful is essentially saying that you are going to have a large mean squared error or a large sum of square block. A large sum of square block or a large sum of mean square block, because that would indicate information getting pulled out of the error. So we could look at the CRBD ANOVA table and basically say, okay, well, you know, the sum of square for the block and the mean square for the block are quite small. This might indicate that blocking is not useful, but it's better to have a formal test about the block effect, so we actually can, you know, state with some clarity whether or not blocking has been effective in the particular experiment. And we can do that simply by structuring a hypothesis test about the block effect. So logically, blocking being useful means that there's going to be a big sum of square block and a big mean square block, because that's indicating information getting pulled out of the error. And if sum of square block and mean square block are small, that would mean the opposite. But again, from a statistical point of view, what does it mean to be too big or too small? We can build a hypothesis test where we actually have a cutoff based off of a significance level or a critical value, and we can use that cutoff to determine if the effect is useful or not. So to do that, we run an effect or a hypothesis test about the block effect. And this is going to be done in pretty much the exact same way that we ran the hypothesis test about the treatment effect. We're just using the second row of our CRBD ANOVA table. Okay, so here we would say, assume all assumptions are intact. And these are the same assumptions for the hypothesis test about the treatment. So everything that comes out of the CRBD whether it's a hypothesis test for treatment, for block, or a multiple comparison, they're all going to use the same assumptions. Okay, and then we would proceed in the usual way. So there's a few ways that we can do this. For example, we could write beta 1 equals beta 2 equals beta 3 equals beta 4. This would be blocking was not effective. Okay. And then we can put this against the opposing. So at, or rather, not all block means are equal. So this would be blocking was effective, right? And then on step 2, we can state the significance level. There's no significance level given, so we'll just use the standard 0.05. Then on step 3, we're going to have our F statistic for the block. So this is going to be MS block divided by MSE. All right, and from the ANOVA table, that's going to be 65.67 divided by 7.2. All right, and that is equal to 9.12083. All right. Okay, so then on step 4, we can take the p-value approach or the critical value approach. Probably have time just to get one of these done. All right, so this is an F test. So this is going to be an F on 0.05, 3, and 15. All right, so if we pop open one of the ANOVA tables here, or one of the F tables here, 315, try this one. Okay, so here's 3. Here's 15, 0.05. So that gives us a critical value of 3.29. All right. And then we can see our F statistic is inside the crit rejection region, so we would reject 0. All right, so I'll stop there. Okay, so you should be getting the email invite to CrowdMark momentarily. I will be available for questions in the office hour room. If I don't get to you right away, it's because there's another student in the room. Otherwise, I will let you in for your question immediately. I will see you there. So good luck, and talk to you guys on Thursday if you don't have any questions.